Hi all, welcome to the lecture 6 part A. In this lecture we are going to discuss about model complexity. Now what is model complexity? Let us start with the simple example where with our empty curve data set where we have on the x-axis we have taken horsepower and on the y-axis we have taken miles per gallon, and this is the scatter plot, and we have fitted this line miles per gallon equal to beta naught plus beta 1 horsepower plus epsilon. Now this is a simple linear line, so this is the line and this is the function that we are trying to fit. Okay, this is a simple line everybody can understand, and what we are seeing that the r square is 0.602 and root mean square error is 3.74. Now r square is 0.602 means that 60% of the total variability of miles per gallon can be explained by this particular model. Okay. Next, we thought like, okay, why not we try a quadratic function, some kind of a horsepower square we add. When we are doing that, what is happening is we just put another engineered feature, horsepower square. So original data is in the 2-dimension, horsepower and miles per gallon. So this was the 2-dimensional data. The data was in 2 dimension, you can imagine. Now we engineered a new dimension, 3rd dimension, and we put the data in the cube, right? And that is what we are trying to fit. Now, if you see that when we are fitting this model, quadratic model, this purple color curve is the quadratic model that we are fitting. This purple color curve is the one we are fitting. Now, and what we seeing that r square has gone up. It was previously in the linear regression, it was 60%, but when we are using quadratic regression, what we are seeing, the r square has gone up to 75%. So which is a good news. And then root mean square also has gone down as expected. So it was about 3.74. Now it is 2.93. So quite a bit of reduction in root mean square error. So what about if we can put quadratic term, we can put also the cubic term. Everything else is same. So beta naught plus beta 1 horsepower, beta 2 horsepower square. Now what we are doing, we have created other than horsepower square, we have created a horsepower cube. So now data is in the 4th dimension. We cannot draw this 4th dimension. Since we cannot draw in the 4th dimension, we only have to imagine how the 4th dimension would look like. So the original data was in the 2 dimension. Now we are putting it into the 4th dimension. We are putting the data as we are engineering new features. Okay, we are engineering new features. We are putting into higher dimension. And as a result, we see r square is now 0.761, 76%. Previously it was 75% in the 2 dimension when we put a quadratic model. when we put a quadratic model, we had 75% accuracy. When now we are doing a cubic polynomial of order 3 or cubic function, we have 76%, and now RMSE 2.903. And the model, if you can see that by adding this new quadratic cubic term along with the quadratic, this blue color is now the main function, whereas and almost they are same. They are almost same, that the quadratic curve and the cubic curve, they almost looks like same, and there is no much importance. But you can, and this is the 3 model. This one is the linear, right? This one was the linear. This one was the quadratic, and this one was a cubic. Now, so remember that my data is always in 2 dimension. Data is 2 dimension. So after linear was also modeled in 2 dimension, but when we went to quadratic, it was put into 3 dimension, right? It was put into 3 dimension. It's 3D. And we went to cubic, it was 4 dimension. The data was our model we put into 4 dimension. So what does it mean? It means we are increasing the complexity of the model. That model is becoming complex, more complex. Now you can tell me that, sir, why I need to stop at 3? I can go up to as many as possible. I can develop a model which is polynomial of order 10. Yeah, you can do that, right? I can develop a model like beta 1 horsepower plus beta 2 horsepower squared plus dot plus a beta 10 horsepower to the power 10 plus epsilon. I can easily fit a polynomial of order 10. Nobody can stop me. But the point is, what is the interpretation? What is the interpretation? What is the interpretation that horsepower to the power 10 has what kind of effect on miles per gallon? Can you explain that? Can you explain this term in your model? Yes, if you fit a more and more complex model with increasing complexity, your predictive accuracy, you can see this, your predictive accuracy will go up. Your root mean square error will go down. You can see that it will keep going down. But as you increase the model complexity, eventually you will see that you will not be able to explain the model, and that is where all problems lies. So you can see that model complexity, that initially we considered this model, that simple linear model, then quadratic model, then we put it into 3 dimension, the cubic model, 4 dimension. The another type of thing, this is also 3 dimension hyperplane, that instead of horsepower and that engineered feature, you put more and more new predictors, weight, displacement. If you have more and more features, you will have a more and more predictive power. So if you put more and more feature or more and more engineered feature, the model complexity will go up. As the model complexity go up, the predictive accuracy goes up, and typically you will see root mean square goes down, which is a good news. But at what cost? The cost is you are paying the explainability. You can't explain the model. Many times model becomes almost like a black box. Now, if you are working in a banking and finance kind of environment, you will see that regulator will always ask question why you need this particular term or why you need this complex model. Can you do the same predictive accuracy with a simpler model, parsimonious model? Right? Similarly, if you're working in the say pharmaceutical company, explainability of the model is extremely important. If you are using very complex model upon which your drug approval is depending upon, and you cannot explain the model what is happening, then there are a lot of ethical issue comes into the picture. So therefore, people prefer a model which is less complex but good accuracy, good predictive accuracy is being achieved. So with higher order regression, high model complexity, you can fit any model of order P as Y as we have discussed. So any polynomial of order P. Similarly, you can put sine cosine functions of increasing frequency, say beta 1, beta 2, sine omega xi, cos 3 omega xi, sine 2 omega xi. If you feel like your data has a lot of sinusoidal behavior, then this kind of Fourier models, Fourier with Fourier terms helps a lot. Now here, if you know the omega, if you know the value of omega, then you can fit this model in using simple OLS method. Because if you know the value of omega, then you know what will be the omega xi, you know what is the sine omega xi. If you know the omega, then you know omega xi, you know what is cos omega xi. Similarly, all these terms are known to you, right? And now, as you know all these functions, so that means if the model is linear in parameter, this is very important. Your model has to be linear in parameter and feature part has to be completely known. If your engineered feature, these are all the engineered feature or transformed variable, you can call it transformed variable. The transform variable part shouldn't include any unknown component. Your feature engineered part should not include any unknown component. If your engineered feature is completely known, then the model is linear in parameter and you can use simple ordinary least square method to fit the model, train the model, do the prediction. You can do everything. But the problem is, as you put more and more engineered feature, the model becomes highly complex. You lose the interpretability and explainability of the model. So, some remarks. The simple least square method can be adopted for any model which is linear in parameter. This is very important. The model has to be linear in parameter. Okay. As P, the number of feature, a number of predictors, or the order of the polynomial increases, model complexity increases. P is the number of feature or the number of column in your design matrix. Okay, so typically it is n cross P. So P is the number of predictors or the number of feature in your design matrix. As it increases, your model complexity increases. What happens? Now there is a big question. What happens when model complexity increases too much? Let us try to understand what happens when model complexity increases too much. Obviously, one loses interpretability and explainability. But in order to answer this question, first try to understand two concepts. One is bias. Another is variance. So, what is bias? If theta is unknown, and theta hat is an estimator of theta, then if expectation of theta hat is equal to theta plus b, then b is known as bias. So b is the bias. Okay, and theta hat is, and if b is 0, if your bias is 0, then theta is known as unbiased estimator. Okay. Now what is variance? The variance of theta hat is expected value of theta hat minus expected value of theta hat whole square. So this is typically what you will see the definition of bias of estimator and variance of estimator in statistics. Now, in machine learning or statistical machine learning, it is slightly different. Okay, let us try to understand. I mean, it is the same concept, slightly, context is slightly different. Let us do it little slowly. Okay, if you want, you can do it slowly, or you can repeat the video, this part, because this concept is subtly different. Same concept, but subtly different. Consider the prediction of new response at input x0. So x0 is a new response. Okay, new response, and y0 is the f of x0 plus epsilon naught. So now x0 transpose beta hat is, we can call it f hat x0, is an estimator of f of x0, which is x0 transpose beta. So x0 transpose beta hat is an estimator of x0 transpose beta. Okay, now what is how the bias variance behaves? Now suppose this is the point for which you want to do the estimation. So true f of x0 is suppose here, this rate point. Okay, this rate point is true value f of x0. This is true f of x0. Now this blue point is f hat x0. So naturally you have this difference can be viewed as a bias. This difference is viewed as bias, and this red line can be viewed as variance of f hat x0. Now what is this blue line? Sorry, this blue line, previously I said red line. So blue line, this blue line gives you that, okay, this could be the prediction. So let me just little bit erase this part. Okay. So this could be the prediction, but this is the actual value, a confidence interval, actual prediction could be anywhere in this range. So the variance of the confidence in the prediction is very less. So that is the variability, possible variability is very high. So this is a high bias and high variance situation. Now I am talking about high bias but low variance. So similar thing, you can see this is a true f of x0, this is if hat, this is estimated f hat x0, this is true f x0, and if you see this, the variability is so less that very tight and lot of bias. Now what is happening, you can see that bias is almost null. There is almost no bias. This is a low bias situation, but very high variability. My confidence in my prediction is very less. The variability of my possible prediction could be anywhere in this region. Whereas this is the low variance, low bias situation. We obviously would like to arrive somewhere in this situation. This is probably the best situation where we have low bias and low variance situation. However, here is the bad news that I am bringing to you. The bad news is that we cannot, given a fixed sample size, given fixed sample size for training, say n, training or fitting, whatever you call it, given this fixed sample size, if you try to reduce bias too much, your variance will shoot up. If you try to reduce variance too much, your bias will shoot up. This is typically the case. So what people try to do is they first try to define bias and variance with respect to mean square error. So this result mean square error is a function of variance of x naught beta hat and bias square. So how it is started, definition of a mean square error of f hat x naught is y naught hat minus f of x naught whole square, and then with some algebra, with a little bit of algebra, you can show that this is equal to variance of y naught hat plus bias square. Okay, and I'm not going into the derivation of this mathematics. I'm just going to use this result. Okay, I'm going to use this result. I think in the Tipshirani's book of Elements of Statistical Learning, you can find the derivation. If you are interested, you can have a look into the textbook. Now, what I'm planning is to have a look how typically it behaves. Now, if you see, if you consider a model whose model complexity increases, what happens that the variance with the increasing model complexity, the bias typically goes down and variance typically goes up. And because mean square error is a function of variance plus bias square, so what happens, it first goes down, comes to some kind of minimum, and then it starts going up. So instead of trying to minimizing bias and variance together, what we try to do, we try to minimize the mean square error. And perhaps this is a parsimonious model where we want to stop. We don't want to increase the model complexity any further. Okay, this is typically how the model training happens. I'll stop here. In the next video, we will discuss the technique of variable selection, also known as feature selection, to achieve a parsimonious model with reasonable complexity. So we will talk about it, that as instead of using all the features and all the possible engineered features, we'll drop some of them and try to come up with some reasonable number of features in the model and try to arrive some kind of a parsimonious level somewhere here where mean square error is minimum and bias and variance is somewhere in the controlled level and not too high, not too low. Okay, thank you very much. See you in the next video.